Hello to all my viewers. This is Dr. Dhaval Maheta, and today we'll understand how to run regression analysis with categorical variable in STATA. Regression analysis is a powerful statistical method used to model the relationship between dependent variable y and one or more independent variables such as x1, x2 till xk. A regression model assumes that all independent variables are continuous, such as height, income, and temperature. Now, what if our independent variable is categorical? The example is race, industry, country, treatment group. A categorical variable does not fit these assumptions naturally. That is the assumption of regression analysis. As we cannot code undergraduates, graduates, and postgraduates directly into the regression equation. So how to solve this problem? Dummy variables will solve this problem by converting a categorical variable into series of dummy, there is 0, 1 variables that a regression model can understand. Key assumptions of regression analysis. First, linearity. The relationship between predictors and the outcome variables should be linear. Normality. The residuals, that is the error distribution, should follow a normal curve. Or in other words, the residuals should follow a normal distribution. Homoscedasticity, constant variance. The variance of the errors should remain consistent across all levels of the predictors. Independence. The errors for one observation should not be correlated with those of another. Correct model specification. The model must include all relevant variables and exclude irrelevant ones to avoid the bias. Now, what is the equation for general linear regression model with the dummies? So y is equal to beta 0 plus beta 1 x1. So the coefficient of x1 is beta 1, coefficient of x2 is beta 2 till beta k xk, and gamma is the coefficient of the dummies. So gamma 1 d1, gamma 2 d2, gamma m dm, and epsilon is the error term. So there is one question, that how many dummies should be introduced in our regression? For categorical variable with L labels, we always create L minus 1 dummy variables to avoid the dummy variable trap. This we will see in the next slide also, that is to avoid the perfect multicollinearity. So suppose occupation has 3 categories, teacher, engineer, and doctor. So we need 3 minus 1. 1, 2, 3. 3 minus 1 is equal to 2 dummy variables. One category will be the base group. So teacher becomes the base group. See, arbitrarily, we can select any one as a base group. The omitted category becomes a reference group. So let's say we have created the dummy for engineer, dummy for doctors. So the category whose dummy is not created becomes a reference group. Teacher, 0, 0. Engineer. So this is a dummy for engineer. So we will write here 1 and here 0. Doctor, 0. And this is a dummy for doctor. So we will write here 1. So here teacher is a reference category. Now when we will run the equation, see, let's see the previous equation. Dummy for engineer and dummy for doctor. The reference category is teacher. So gamma 1 and gamma 2. So what will gamma 1 give us? It's a coefficient of dummy 1. So it will tell us how much engineers differ from teachers in the dependent variable. Gamma 2, coefficient of dummy 2, how much doctors differ from teachers. What is a dummy variable trap? The dummy variable trap occurs when we include all the dummy variables for a categorical variable along with the intercept in the regression model. So all the dummies have been introduced, D1, D2, and D3, all have been introduced. So what will happen? This creates a perfect multicollinearity. One variable becomes a perfect linear combination of others, making it impossible for regression to estimate coefficients uniquely. Now, see how it can happen. We have 3 occupations, teacher, engineer, and doctor, and we have created 3 dummies, teacher, engineer, and doctor. Now if we do the summation of it, it is 1. This means one dummy is a perfect linear combination of others and they intercept. And this will create a major problem of multicollinearity. We cannot run this equation. Now we will take one example. Let's go in STATA. So I'll write here sys use auto. No, not auto. Use sys use NLSW 88. So on right hand side, you can see the name of the variables, but still I insist that you run the command browse to see the entire data frame. So the categorical variable is race, married, never married, graduate, college graduate, South, SMSEA, CT, industry, occupation, union. Okay. And at the fag end, we are having wages, hours, total experience, tenure. We will consider the wage as a dependent variable. Please listen carefully. Wage as a dependent variable. And the independent variable is hours, total experience, tenure, and one categorical variable which we want to introduce is the employee member of union or not? This is one categorical variable. In this, we are having two levels, 1 and 2. So if we are having two levels, how many dummy we will create? Yes, you are right. We will create 2 minus 1. That is, one dummy will be created. What will be our general equation? Wages is equal to beta 1 hours plus beta 2 tenure plus beta 2 experience, total experience, plus gamma 1 D union plus epsilon. Wage is our dependent variable, as we have already discussed. Hours is how much hours the employee is working, tenure, experience. Now just focus on D union. If an employee is a member of the union, it is indicated by 1, and if the employee is not the member of union, indicated by 0. So D union will either take the value 1 or it will take the value 0. Okay, let's proceed with this. Now we will run the t-test for individual regression coefficients. The t-test checks whether a single predictor significantly contributes to the model or not. The null hypothesis is bj is equal to 0. That is, a predictor xj has no effect on y. Alternative is bj is not equal to 0. That is, a predictor xj has a significant effect on y. If the p-value is less than 0.05, we reject null, which means that the predictors are statistically significant. Now, what is desirable in case of t-test? Please remember, the p-value should be less than 0.05. Then only we can say that the predictors are statistically significant, or in other words, the independent variable is affecting dependent variable significantly. So in case of t-test, p-value less than 0.05. Same is the case with ANOVA. ANOVA framework in regression uses the F-test to check whether the model explains significant amount of variation in y or not. What is the difference between t-test and ANOVA? T-test checks the individual contribution. That is the individual contribution of the independent variable. Let's see this equation. Wage is affected by hours, tenure, and experience. So t-test will check individually that is hour contributing, yes or no, is tenure contributing, yes or no, is experience contributing, yes or no. So this is for t-test. ANOVA is joint contribution, that hours, tenure, and experience, are they jointly affecting wage or not? Okay, so what will be our null? Null is beta 1 equal to beta 2 till beta k is equal to 0. So none of the predictors explain variation in y. Alternative, at least one bj is not equal to 0. So the model with predictors explain more variation than the intercept only model. Now what does it mean? The model with predictors, it means that the predictors are significant. What is desirable? Desirable is The F statistics should be significant. How it can become significant? P value should be again less than 0.05. Then the regression model as a whole is meaningful. See, what is the another way in which I can write null hypothesis? Model does not exist. Alternative, model exists. So desirable is that we reject null. This can be only done if the p-value is less than 0.05. Now we will run this equation: regress, wage, hours, total experience, tenure, and I dot union, because we want to create the dummies. So enter. We got the output for hours, its p-value. Total experience, its p-value. Tenure, its p-value. And is the employee member of the union? Yes. Then its p-value. F statistics, its p-value, r square, and adjusted r square. Now let's do the interpretation. We'll start first with the model fit. Is model fitting or not? So this p-value is, as we have discussed for ANOVA, it's the same thing. As a p-value of F test is 0.00, which is less than 0.05. So the overall regression model is highly statistically significant. This means that the combination of hours, total experience, tenure, and union status has a significant explanatory power for predicting wage. Wage is our dependent variable. The model explains 15.3%. This explains 15.3% of the variation in the wages. This leaves 84.7% of the variance explained by other factors not included in the model. No need to worry. See this, why this is less? Because possibly it, education, industry, occupation, location, gender may be affecting it. Okay, let's proceed. Now we will do the interpretation for the regression coefficient. This one. We start with the intercept. Its value is 2.691. P-value less than 0.001. Its p-value is less than 0.05. Okay. So as the p-value is 0.00, which is less than 5% level of significance, intercept is significant, which means that predicted hourly wages 2.69 for a non-union employee. Why non-union? Because everything is zero. The hours are zero, total experience is zero, tenure is zero, and not the member of union. Then only constant exists. So for a non-union employee who has a 0 hours worked per week, 0 years of total work experience, and 0 years of tenure at the current job, so this value often serves as a mathematical baseline for the model. This situation cannot exist, but it's a baseline for comparison. Now let's talk about the hours. This one. Hours, it is 0.0191, p-value 0.038. What we will write? As the p-value is 0.038, which is less than 0.05, so definitely wages affect. So definitely, yeah, I have included the word working. So definitely working hours affects wages of the employee. Holding union status, that is a member of union, total experience, and job tenure constant for each additional hour worked per week, the hourly wage is predicted to increase by 1.91. So it's very simple, multiply it by 100. Holding all others constant, the increase, that is if the employees work 1 hour more, so they will gain 1.91 cents more on an average. This is a very small effect. It might reflect that the employees who work more hours, example full-time versus part-time, get a slight premium, but the primary drivers of wages are others. This is not a primary driver. There is other. Which is the other primary driver? Let's see. Total experience. This one. So as the p-value of this is 0.00, this one, which is less than 0.05. So total experience definitely affects wages of the employee. holding union status constant, hours work constant, and job tenure constant for each additional year of total work experience here, with 1 year increase in experience. Hourly wage is predicted to increase by $0.28 on average. This is a strong positive effect. It means that the experience is a major driver of wages. A worker with 10 more years of experience can expect 10 more. So multiplied by 10, expect to earn about 2.78 more per hour. All else are equal. Keeping all else equal. What is the effect of tenure? This one. Its p-value is less than 0.05. So what we will write, as the p-value is 0.00, which is less than 0.05. So tenure definitely affects wages of the employee. Holding union status, hours worked, and total experience constant for each additional year of tenure at their current job, hourly wage is predicted to increase by 4.69 cents on average. This is also a very small effect. Now, what about the union membership? See, union membership 1.19. So as the p-value is 0.00, which is less than 0.05, so being a member of union definitely affects the wages of an employee. Holding hours worked, total experience, and job tenure constant, union members earn on an average. So if the employee is a member of the union, so on an average they are earning $1.1 more per hour than non-union members. It is the second largest effect in the model. This means that the collective bargaining power of union leads to a higher wages for members. Now, what is the equation which is formed? Let's see. First of all, see the general equation which we had made. Yeah, this one. Wage is equal to beta 1 hours plus beta 2 tenure plus beta 3 experience plus gamma 1 D union plus epsilon. So the equation which we got is this one. Wage is equal to 2.69 plus 0.019 hours plus 0.278 total experience plus 0.04 tenure plus 1.19 D union plus epsilon. This equation we created from here. So you can see 2.69, 1.19, 0.046, 0.278, 0.19, 0.0191. Now what will be the equation for non-union employees? So this will become 0 and our equation will be 2.69 plus 0.019 hours plus 0.278 total experience plus 0.046 tenure. This part will not be there. Now what about those who are the members of union? Equal to 1. So this will become 1. So this is 1.190 and it will get added to the constant 2.69 plus 1.190. So it is 3.88. So on an average, the employees who are the member of the union get the wages 1.19 extra. Whatever output which we have generated with the help of command user interface, the same I can also generate with the help of graphic user interface. So go in linear models, linear regression, done. Click here, activate wage. What will be my independent variable? Let's pick it up. Hours, total experience, tenure, I dot, you'll have to write here I dot union and press submit. See, I'll get the same output. Okay, I'll get the same output. Let's go again to the slides. We'll have to check the normality of the residuals. So normality of the residuals is an assumption needed mainly for valid hypothesis testing and confidence intervals. So first we'll run predict resid and residuals to store the residuals, and then we will check the normality with the following commands. So first we will generate QQ plot by the command line qnorm resid, then PP plot with pnorm resid, and then histogram. Okay, let's go in the STATA. Predict resid residuals, enter. Now Q norm, resid, enter. So if the residuals are normally distributed, all the blue dots will be on this straight line, but they are not. So there is a deviation from the normality. Okay. Let's run the another command, p norm, resid. So same is the scenario here also. The blue dots are not on the black straight line, but we will run a formal Sapir-Whorf test. So this is the p-value. What will be my interpretation? The null hypothesis is the residuals are normally distributed. Alternative, the residuals are not normally distributed. This is a command, and this is a p-value. In case of residual testing, please remember, in case of residual testing, either it is a normality testing, either it is a autocorrelation testing, or it is a heteroscedasticity testing. P-value should be more than 0.05. It's opposite of the model fit. In model fit, for t-test and ANOVA, p-value should be less than 0.05. In case of residual testing, the p-value should be more than 0.05. So here, as the p-value is 0.00, which is less than 5% level of significance, so we conclude that the residuals in the model are not normally distributed. So this is not desirable. This is not good. Okay. Next is the multicollinearity. So multicollinearity is a statistical phenomena in which two or more independent variables in a multiple regression model are highly correlated. So this is a command, VIF, and let's run this command also. Now right here, VIF, enter, and we got the variance inflation factor. Now let's do the interpretation of this also. The variance inflation factor results indicate no concerning multicollinearity among the independent variables in the regression model. All VIF values are well below the common threshold of 5. And the mean VIF is very, very low. This is also good. This means that the predicted variables are not highly correlated with each other, and the estimated regression coefficients are stable and reliable. So this is good. Normality assumption was violated. That was not good. Now let's talk about the heteroscedasticity. So what is our null? Residuals are homoscedastic. The variance of the error terms is constant. Alternative, they are not constant, or it is a heteroscedasticity. The variance of the error term is not constant. It depends on the value of the independent variable. So we will run these two commands to check. So for this RVF plot, you can see there is some increase in variance. See this, there is some increase in variance. So we will have to run the formal test for it. So right here, head test, enter. We got the results. This is a result of Bruce-Pagan test. This is a p-value. Now let's do the interpretation for it. The p-value of this test is 0.00, which is far less than 0.05 threshold. Therefore, we decisively reject the null hypothesis of constant variance. The test confirms that the error variance in the model is not constant and is related to the magnitude of the fitted values. This is not good. This is not desirable. Okay. Next is information matrix test. So this, the null hypothesis states that the standard assumptions of the classical linear regression model or the maximum likelihood model are valid. And for this, we will run the command imtest, white. So I'll go here, imtest. So we got the results. Null is homoscedastic, alternative is unrestricted heteroscedasticity. P-value for heteroscedasticity is 2ness kurtosis, and this is the joint test. So we'll have to see the joint p-value. Let's do the interpretation. Information metric test is an overall test that combines the heteroscedasticity, skewness, and kurtosis test. If the information matrix test is significant, it means that this equivalence does not hold. This failure can be caused by one or more forms of model misspecification. So either the problem is because of heteroscedasticity, skewness, or kurtosis. As a p-value of IM test is less than 0.05, so the result confirms that the joint information matrix of the model is invalid, meaning the standard errors and test statistics cannot be trusted. Now, whatever output which we have generated for residuals, the same you can generate with the help of graphic user interface also. So go in statistics, linear, regression diagnostics, specification test. Click here. So in this, first is test for heteroscedasticity. Just press submit and we got the result. Information matrix test, submit. Then here we are also having the VIF. Click here, submit. Okay, cancel this. The same thing I can generate from statistics, post estimation. First of all, click on diagnostics and analytics plot. Diagnostic and analytic plot. Click here, launch. Just click submit and we will get RVF plot. Close it. Now click on this specification diagnostics, test for heteroscedasticity, launch, and we will get the same interface. So test for heteroscedasticity, information matrix, and here is the VI. So this was all about how you can run regression analysis with categorical variables in STATA. For more videos on STATA, kindly refer to my playlist. I have also uploaded many videos on data science, machine learning, and artificial intelligence on my YouTube channel named Dhaval Maheta. To watch the full videos, please subscribe to my YouTube channel and check the playlist. Please don't forget to like and share my videos. You can also follow me on different social medias. Link given in the description box.